Yeah. Okay. So very good afternoon to all of you. Today we have a 60th Ananthakrishnan Colloquium. Today we have an eminent speaker with us. So let me introduce the speaker and welcome him. His name is Dr. Ashish Bhole, and he is a mechanical engineer by academics and a PhD he has done in University Côte d'Azur, Nice, France. And then his research interests are basically focused on developing efficient computational methods and parallel computing algorithms for solving PDEs and arising in mechanics and physics and many other problems that especially atmospheric ocean science. So his research activities has a strong interdisciplinary aspects such as plasma physics, fluid mechanics, environmental problems, geophysical flows, electrostatic media, etc. So they rely on physical models described by PDEs, obviously, and his goal is to create better, efficient, accurate parallel algorithms for them. I think it is a very interesting topic and very relevant to all our model activities also. So with this short introduction, I welcome you to deliver the colloquium. Welcome. By PDEs, obviously, and his goal is to create better, efficient, accurate parallel algorithms for them. I think it is a very interesting topic and very relevant to all our.
Thank you very much for the introduction. I am postdoctoral researcher in Sweden at KTH, but the works that I will present today are not from here. They are from my previous positions, and they are about PDE modelings. So the many problems that arise in physics, mechanics, different branch of engineering, atmospheric sciences, climate sciences, even finance, they can be modeled mathematically as partial differential equations, where R here is partial differential equation compactly written as a residual. But we are particularly interested in hyperbolic modeling, where the physics terms or physics characteristics could be transient phenomena, convective phenomena. There may be some parabolic part from diffusive phenomena, and there may be some reactive or source terms. So this is very generalized framework, very general modeling. They these partial differential equations provide framework for large class of problems. And we are interested in solving this problem for W. W is vector of variables depending on which physics or which problem we are solving. And the analytical method of mathematics are not developed enough so that we every time find this W analytically in the closed form. There may be another approach to study the problems at hand using experimental techniques, but those experimental studies may be limited by cost or limitations of the measurement. So in that case, there is a third possibility, third option that we prefer to go for is the computational method or numerical method. The approach is that we discretize this partial differential equation we discretize this partial differential equation and we look for approximate solutions. So what we ask to our numerical methods to get those approximate solutions. First, we want that our approximate solutions are as accurate as possible. So how can we achieve that high accuracy? We may ask our discrete equations, approximate equations and approximate methods that can they satisfy some certain physical properties of underlying physics? Can they incorporate some mathematical aspects of underlying partial differential equations? Can they take advantage of geometry of the underlying problem. But these aspects can give us high accuracy. Of course, it is not so straightforward to achieve the high accuracy in most of the cases. But nowadays, high accuracy is no one cares on if you are only highly accurate. It is equally important that the high accurate methods are also high performant method. So what we do for that, we try to see if the methods are high resolution, if they have high resolution capabilities, if they can be deployed on massively parallel supercomputers, if we can optimize meshing, and there may be many other factors. But when it comes to hyperbolic partial differential equations, there is some set of problems that usually we are interested in. So hyperbolic partial differential equations are known to have wave-like solutions.
Convective problem.
Yes, they are mostly advective or convective problems.
Hyperbolic or diffusive.
Diffusive problems. And the hyperbolic problems, or the problems which are hyperbolic dominated or convection dominated, they contain wave-like solution. And in computing, in simulations, there can be dispersion errors. So this is the first challenge we have to face when we discretize hyperbolic partial differential equations. Then there can be nonlinear terms. Perhaps you may be familiar with fluid dynamical equations. They are nonlinear and they give rise to phenomena like turbulence. Nonlinearity can also lead to development of shocks in the flows, discontinuities in the flows, and discontinuities give rise to different kind of challenges in the numerical methods. So I'm going to present some of my projects, couple of them very quickly, and one on plasma physics in bit depth. And I will highlight the key ideas that how we tackle these problems along the way. So in all cases, our goal is to achieve high accuracy along with high performance. So the first part is finite difference methods for compressible flows. So what are finite difference methods? In finite difference methods, we consider a domain, we discretize a domain. Let's say we have 1D domain, simple 1D domain, and we have discretized that domain with k points. So we have total k number of points, and we are approximating our function or variable we are solving for at these k points, and we evolve these k points using numerical algorithms. So for fluid mechanical problems, one of the simplest model problem that we can think of is linear advection equation. What it says that any signal u is traveling with constant speed c. But this is the reality, or this is the model problem. In numerics, this does not happen. In numerics, the approximate solution un travels with the speed which is may not be same as c, which will be something else. Let's call it as numerical speed. And this numerical speed may be function of wave number. So what it means that such computation of such equations lead to dispersive solutions, and which we do not want. So one way to construct the accurate numerical method is to look at the dispersion relation of this equation. So dispersion relation is we look at the wave number and frequency domain. So this is the dispersion relation of this equation, where omega is wave frequency and k is wave number and c is this speed. And if we can devise such numerical method that can preserve this dispersion relation, then we are expected to achieve high accuracy or high resolution. The same analysis can also be performed on parabolic equations. Here I have written, I have written the equation, heat equation, dispersion relation for that, and we can draw similar conclusion that if we want to achieve high order accuracy method to solve heat equations, then we should have a numerical method that can preserve this diffusivity close to ideal one. But let us not worry about parabolic part. Let us worry about only hyperbolic equations right now. So these are the compressible 2D compressible flow equations written compactly. Model problem for them is linear advection equation. The idea is to construct the numerical methods that can preserve dispersion relation for linear model problem, and then we apply those methods here to discretize these derivatives. So those methods they are family of compact finite difference methods. One of them is optimized upwind compact scheme, which is whose coefficients are uh, tuned or optimized to preserve the dispersion relation, and that's why we see high resolution here. So what this figure shows that x-axis is normalized wave number in our computations, and y-axis denotes how accurately the numerical derivatives are resolved. So for long range of wave numbers, we have near accurate uh, resolution capabilities. And then along with high order Runge-Kutta methods, uh, the combination of compact finite difference methods and high order Runge-Kutta methods give us dispersion relation preserving methods. Then in fluid mechanical problem, these terms are convective terms are nonlinear. They can develop shocks. That's why we need to treat them separately. And finally, when we construct algorithm for that, it is serial. The first algorithm is serial. It takes very long time to compute realistic flows, and we have to use domain decomposition method to deploy that algorithm on the HPC. So some of the applications of that solver of this work is on, I have shown it here. So first one is transonic flows. So this figure shows the pressure distribution of transonic flow over 2D airfoil. X-axis is the normalized chord of airfoil, and y-axis, the quantity on y-axis denotes pressure distribution. And we can see the computational and experimental results match exactly, and this jump is the location of shock. These transonic flows are very challenging to compute in aerodynamics, and since we are using dispersion relation preserving method, we can accurately capture this flow physics here. On the other hand, while these are high speed flows, we have also applied those methods for low speed flows. So these are the pictures of Rayleigh-Taylor's instability simulation, may be relevant to atmospheric sciences community, where heavier fluid rests on the top fluid, heavier fluid rests on the lighter fluid, and instability developed at the interface, and this is how it evolves. So I'm not going into details. I just wanted to show that these methods are capable of simulating flow physics in the diverse range.
To develop the code and put on the GitHub. The slide you are writing here.
Oh, that. Sorry. So the actual CFD solver itself is not on GitHub, but this is the analysis of finite difference methods. This figure shows the analysis of finite difference methods. On GitHub, I have a code that you can use to spectrally analyze any finite difference method.
All your master thesis.
Yes.
Aerospace, no?
Yes. Yes, this is from aerospace. Then next, I will present my work on shallow water flows using finite volume methods. So approach is slightly different than finite difference methods. In finite difference methods, we saw that domain was discretized and we were interested at looking what happens at the grid points. Now we are interested at what happens at the interval. We still discretize the 1D domain into K cells, and we look at the one particular interval. And so one of the model, probably some of the people at IITM might be using, are shallow water flows.
We use
So-
three-dimensional models for shallow water.
Yeah. So if we want to study large bodies of water, let's say ocean, then there are shallow water equations which are 2D that can be derived from 3D Navier-Stokes equations using depth averaging. So here is the sketch of, let's say, large water body, let's say ocean, where vertical dimension is significantly lower than horizontal dimension. So what is done in this case, that Navier-Stokes or Euler's equations are depth averaged in this direction. This D may be bottom topography, let's say bottom of the D. And then the equations are derived in terms of H, height of the water body, and depth averaged momentum. So this is 2D model, and this model is written mathematically as in the conservative form. And there has been a lot of development in the finite volume community to numerically solve such method. One of the good reference is here, but this model comes with certain limitations. So in this sketch, we are looking at the sketch for Brock's experiment, where he studied the flowing water train on the slanted surface. And what he noticed, that in the water waves, there is some plateau here. We see similar wave trends when we see rainwater flowing on the slanted surface. So what shallow water models cannot reproduce is this slanted plateau at the top. And the reason for that shallow water equations ignore classical shallow water equations ignore the second order velocity fluctuations. And when we incorporate them, we get extended model that is mathematically written into cannot be written into conservative form. It has to be written into non-conservative form, and development of numerical methods of such models is further challenging. So P here is a stress tensor that takes into account shear effect that was neglected from the classical shallow water flows. We developed the first order finite volume method for this equation, and this is the effect. So in this 1D simulation, we tried to mimic the Brock's experiment, where we have bottom topography or bottom of the fluid given by this geometry. So we have simply a slanted water bed. The H is perturbed using some perturbation. Velocity is specified to mimic the Brock's experiment. And here we can see that the dotted lines are from experimental data, and the green curve is from extended shallow water equations model. They capture that top plateau quite well, while classical shear shallow water models cannot capture it. So what is the advantage of this work? Now we have more accurate modeling for predictions like tsunami, river flows, landslides, and furthermore, this finite volume method is also applicable for unstructured grids. So the works previous to this were done for structured grids, and one of the target application for this work is this bottom topography. Every time bottom topography cannot be only slanted plane; it can be maybe as complex as this. So ability of performing computation of unstructured grids gives us this advantage, but this solver has not been uh, parallelized yet. So we do not have high performance capabilities on this solver. If some of you, if any of you are interested to take a look, the code is available here. I can share the link. Then let's look at
in the previous H is
Yes.
the topography of the problem.
the height of the problem. Yes, and
Right.
yes, and topography of bottom topography is D. Yeah, and that's why it is tan theta, simply at an angle. Let's look at an exciting problem. Now I will go a bit deep into that. And now the numerical methods are finite element methods. They are different than finite difference and volume methods. We are still looking at what happens at one interval in the discretized 1D domain. But now the solution is represented by polynomial inside this domain. So we are concerned with fusion plasma modeling. You must have read in the media articles that uh, scientists are trying to mimic the sun on the earth. Scientists are trying to build artificial sun on the earth. So what it means that scientists are trying to build fusion reactors that, and those reactors use the mechanism by which sun generates the energy, and that mechanism is depicted here. So we have two hydrogen isotopes. They combine together under extreme situations. I'll come to them, and they generate some particles, but we are not interested much into that. We are interested into energy, and this energy is utilized to create to generate electricity. And this source is supposed to be very clean source of energy, and it can potentially address climate change issues. So this is going to be a fuel. Ionized hydrogen is going to be fuel in the fusion reactors, and that fuel has to be very high temperature. That temperatures are almost 10 times higher than sun's core, and that fuel has to remain confined in the fusion reactors. So this is the core of fusion reactor, this complex 3D geometry, and these rings they denote magnetic fields. So these fields apply strong magnetic field with which the plasma is confined in this chamber. And the criteria is this: N is particle density of the plasma, T is temperature, and T is confinement time. So whenever this triple point is very much higher than this number here, the conditions for generating energy is favorable for us. But the challenge is to get this TE as high as possible. TE means confinement time. That means how long we can confine the plasma in the fusion reactors. But this here is a stellarator, very complex configuration. What we are interested in is axisymmetric configuration. So if we simply imagine that this device being axisymmetric, what we get here is this. This is that axisymmetric chamber here. So this is the sketch of ITER, International Thermonuclear Reactor, which is currently being constructed at France. And these two people give us idea of shape of that device. This is one of the most complex engineering project going on right now. And we are interested in this part. In this axisymmetric chamber, there will be plasma, fuel in the plasma state. And here is another sketch to depict that. These balls denote the plasma particles, which are confined in this axisymmetric chamber with the help of external magnetic fields. And aim of the fusion program or the fusion reactor is to keep the plasma confined in this chamber for a long enough time. And this is what scientists are not able to achieve right now. So what happens? What we want ideally is that we start the nuclear reactor, then the plasma current will go up, and then the fusion reactor will remain in operation for long time while it produces energy. And once it produces sufficient energy, it can safely be shut down. This is what we want. But what happens in the practice? During the operation, there are certain plasma instabilities. They are global plasma instabilities they are known as disruptions. They suddenly terminate the plasma pulse. And this termination is so fast that the energy liberated by plasma, they go to the structures, and the entire fusion reactor structures is at the risk of getting damaged. So, but this is not the only instability. There are many plasma instabilities, but this is one of the most critical problem or challenge that international fusion program is facing. So what is done? What is being done right now to avoid this? So first of all, disruptions cannot be avoided. What we can do is we can at the max mitigate them. So how it is done? It can be predicted before their occurrence, and there is a huge scope of artificial intelligence studies here. And once they are detected, we induce artificial disruptions, artificial plasma instability, so that the the fusion reactor can be safely shut down, and in process uh, it can not damage the fusion reactor walls and the structure. So the technology for that is known as disruptions mitigation system. In this case, we are looking at the cross section of tokamak, and these two ports are a part of disruptions mitigation system. What they do is they inject neutral gas in very high amount in the plasma. This injected gas will trigger the artificial disruptions and they will help to safely shut down the fusion reactors. And such interaction of these gases and plasma give rise to highly complex gas plasma interactions. So plasma physics already is very complex. Theoretical tools are not developed enough. Experimental studies they have their own limitations. It is very expensive to perform these experiments. The plasma diagnostic techniques do not provide insights into what is going here. So that's why we need simulation tool to complement all other two aspects, theory and experiments, where we can have insight to plasma instabilities, and the studies can be complemented from all three angles. So this is the physics model that we were interested in developing for gas plasma interaction. So the box terms equated to zero are compressible Navier-Stokes equations. They are simply equation of momentum, continuity, and energy.
Electromagnetic term.
Yes, I'm coming to that. So if we include these terms, they are coupling between equations of Maxwell. They are blue terms are from Maxwell's equation, and this model is known as MHD, magnetohydrodynamics. This is the model that we are going to use to study plasma instabilities in the tokamak. But for this particular problem, what we want is this entire model. This is gas plasma interaction model, and it can be compactly written like this. Again, in the hyperbolic partial differential equation form, where we have transient terms, convective terms, diffusive terms, and reactive terms. So we discretize these models using finite element methods. In Galerkin finite element methods, we take test function and the shape function with which we are discretizing the variable from the same space, and they give rise to central approximations. So what it means that such numerical methods will tend to produce dispersion errors in the computation, and to treat them, we need to stabilize the finite element method algorithm. So we add one contribution to the finite element method algorithm. This is stabilization based on variable multi-scale approach. I will come to that in a moment. What is that? But right now, it is only important thing to note is whenever solution is smooth, this approach works. Whenever there are shocks, we need additional treatment for shock capturing, and this is that additional term. So we have a finite element algorithm here. It produces dispersion error for hyperbolic partial differential equation computation. If the solutions are smooth, we can treat them using L2 stabilization, VMS stabilization. If there are discontinuities, we have shock capturing stabilization. Now, what is variable multiscale stabilization? In any simulation, we have resolved scale and unresolved scale. Because we are making approximations, in the approximation, we resolve something and we cannot resolve something. So in the VMS approach, we have this W star, which mimics the unresolved scales. And this entire term models, it takes into account effect of unresolved scale into the model through the mechanism of numerical stabilization. So I will not go much into much details of this, but only thing here is important that it offers consistency to the algorithm. That means if we refine our grid, the numerical stabilization will go to 0. And the other part is shock capturing stabilization. So this is critically important because in presence of shocks, the underlying numerical algorithm lacks robustness. So the approach here is based on this tau SC. What tau SC does, it detects the shock. In the domain, it detects the shock and adds the numerical stabilization only nearby and nowhere else. And this is why it is very important to design this quantity. Uh, we have taken inspiration from Basi's work in designing this quantity.
The shock based on the magnitude, are this the noise?
So shock is in a sense discontinuity in the grid. So if we have, when we have steep gradients and as the gradient approach 90 degrees, or let's say uh, within two grid points, there is jump in the function, sudden jump in the function. That is usually shock on the grid.
Discontinuity.
Yes, it is sort of discontinuity, but that discontinuity still is at the discrete level in the simulation.
Finite.
It's finite, yes, but even at the finite, level, numerical methods cannot handle such
Tau is
discontinuities.
kind of a scale beyond which it cannot, kind of some spatial scale or something.
Yes, exactly. Yes, yes. So idea is what our grid cannot capture. We try to model that as a stabilization and incorporate it in our algorithm.
It looks like the previous one was a
Yes.
scale where tau is a diffusion.
Yes.
Previous one, however, is a filtering.
The previous one is also it is also stabilization or diffusion, but it is in a way streamwise upwinded.
So is diffusion.
Yes. This is purely diffusion, but adaptive diffusion.
Tau SC is the scale of.
Yes. So what we were interested in is to implement this stabilized finite element method algorithm into the nonlinear MHD code called JOREC. So JOREC is a big European code. It has been under development since more than 20 years, last 20 years. It has been extensively used for tokamak modeling. It uses advanced finite element methods, and I will come back to these. And it solves, historically, it solves for reduced MHD model. What my work led to the contribution on the full MHD model side. The physics model that we shown, which we just in the previous slide, that is full MHD model, and some further approximation lead to reduced MHD model. So what is the difference between them? That if we look at the spectrum of the MHD model, then we get these 7 waves. In the reduced MHD model, we ignore these fastest moving waves. And that's why they offer computational advantages. We don't have to compute for fast moving waves in the reduced MHD model. But there were different motivations to incorporate full MHD models. So here what we see that the implementation of full MHD model behaves as expected. This figure shows how one of the canonical plasma instability known as internal kink mode scales its growth rate with respect to resistivity. So this line is the theoretical estimate, and these dots are the simulation points obtained using full and reduced MHD models. So what this figure shows that implemented full MHD algorithm gives the physical results, and it also converges with expected order of accuracy. This figure shows the computation of another canonical plasma instability known as tearing mode uh, on the different grid resolution. As we resolve the grid, the numerical solution converges with expected order of accuracy. So little bit about finite element method of the Jorek. Here we use geometry of the domain. Tokamak is an axisymmetric device. So this periodic direction is phi, and the plane perpendicular, we call it as poloidal plane. Poloidal plane is denoted by C, and toroidal direction is by phi. So we use this decomposition in choosing our finite element space. Finite element space is also decomposed into according to the geometry. The Fourier, the toroidal direction is handled using Fourier representation, and the poloidal plane is discretized using C1 finite element method. Why C1? Because the MHD model may contain third order derivative terms, and C0 conventional C0 finite element methods are not suitable for such models. So this is the finite element method in the poloidal plane. We use Jorek uses isoparametric formula of finite element method. What it means that we use the same basis function to represent the grid also. So W are the physics variables and C are the grid representation, and we use the same basis functions. And since we are using bicubic basis functions, we can use this geometry to construct curved cells. Now, why do we need curved cells? Because it is well known in the computational community that if our grid is aligned to certain flow features, we get computational advantages. So here we have cross section of tokamak. This denotes plasma equilibrium, some flow feature. What it means that plasma particle motion is restricted or bound to these closed curves, and that's why we want to construct a grid which mimics these flux surfaces. They are, in physics terms, they are known as flux surfaces. Because these curves are given by partial differential, they are solution to partial differential equations, and to accurately construct grid around them, we needed isoparametric formulation. So, but there are some difficulties in these grids. There are some geometrically singular points, and what happens at those geometrically singular points is this. So, if I plot shape functions at polar grid center, they look like this. So, at each vertex, this is the characteristic of this finite element method, that at each vertex there are 4 shape functions, but 2 of them are oscillatory in the original finite element method, and this leads to the numerical noise. This has been known problem in Jorek simulations. People used to treat this problem by adding numerical stabilization here, but whenever flow or physics was interested, investigation was interested here, that was not a good solution. We proposed a transformation of shape function that treats this problem. In our new transformation, instead of 4, we only need 3 basis functions. They are smooth, and if we repeat this tearing mode simulation, we do not see this noise anymore. Yeah. Yes. Why don't they do it? Yes, it is done, but now instead of one geometrically singular point, there are 4. So what I didn't mention, that this finite element method is well defined only if one vertex in the grid is shared by 4 cells. Not this one. The X point is a saddle point. So whenever one node of the grid is shared by numbers 4 than different, the finite element method is not well defined. And we are currently investigating what is happening at other grid singularities. So now I will quickly go through numerical results to demonstrate the stabilized finite element algorithms on the range of different problems. So this is the nonlinear Burger's equation, and the initial condition is given by 4 constant states. This is rotating wave problem, one of the most challenging problem for computational methods. The initial condition again has jump here. What is expected from these computations is that they develop very complex wave structures like this, and they can only be captured with stabilized algorithms. So what we expect that at the location of these shock waves, numerical stabilization should act and nowhere else. And this is what we see here. These figures in these plots, I have plotted the coefficient of shock capturing stabilization. And we can see that it is active only near shocks and nowhere else. For this particular case, for Burger's equation, we have availability of exact solution that allows us to perform some convergence studies, and we see that stabilization finite element method is accurate and robust. One more challenging problem from which is of interest to astrophysics community. It deals with 2D ideal MHD equations. No, it is known as Orszag-Stang vortex test. It starts with very smooth initial condition. Later on develops shocks. These shocks interact with each other, and that's why That's why this simulation offers challenges to high resolution methods. What we see here, this is the algorithm that uses only VMS stabilization, not shock capturing, and around time t is equal to 1.8, we see some numerical oscillations and the simulation do not proceed ahead. Here, with shock capturing stabilization, this problem is cured. Then, oops. Oh, one slide is missing. But don't worry. The next slide was to show what happens in long run simulation. Using the stabilized finite element method algorithm, we can get these numerical solution up to time t is equal to 0.5 on very coarse grids, the grids as coarse as 100 by 100, while usually in the literature, the grid size of the order thousands are used. So these were the some validations of our algorithm, stabilized algorithm. And now I will quickly demonstrate its use on realistic uh, fusion plasma situation. So this simulation concerns with joint European torus, JET tokamak in UK. It has 80 meter cube of chamber in which there are plasma particles of the order of 10 to the power 20 of the order of 20. Then, as I mentioned earlier, that we are interested in injecting the gas, neutral gas, into the plasma. How we do that, how experimentalists do that, is using the shattered pellet injection. So we have wine cork shaped pellet, this small pellet that contains frozen neon gas, and the number of neon atoms are of the order of 22. So we have ordered 20 particles into 80 meter cube volume, and we have ordered 22 particles in this much of volume. So we can imagine when we introduce the gas into the plasma, the amount of jump in the density variable. So this is how that pellet is shattered, and the shattered particles, the shattered gaseous particles are injected. This is how we are going to model the motion of those particles in the computations. And this simulation corresponds to around 5 million degrees of freedom. Not very much, but it is the iterative solver that take a lot of time, and that's why these simulations take order of 3 to 4 months to finish. So I'll just walk you through what happens in a typical simulation. Here in this figure, I have two planes at 180 degrees apart of the axisymmetric chamber. The color code denotes plasma temperature in the normalized unit. This is plasma equilibrium. We are interested in instability problem. That's why we start with, we initiate the problem using plasma equilibrium. So this is that equilibrium state. The idea is to perturb the plasma using injected gas. So these isosurfaces, it denotes the cloud of gas particles that is formed around the injected fragments. In these figures, I have plotted thermal energy and plasma current versus time. So thermal energy is integrated pressure in the entire domain, and this line here denotes the status of the simulation time. So what happens next in the simulation is here. The cloud is moving inside the plasma as simulation time progresses into the plasma. Now we can see that plasma is no more axisymmetric. Further, this is the effect of instability, disruptive instability, that axisymmetry of the plasma is completely broken. Now there are the plasma has cooled down significantly, and the trigger of disruptive instability, plasma instabilities, has convected that gas in almost in entire computational domain. And this is the end of the simulation that uh, up to which we can simulate. So this simulation cannot be performed without stabilization methods. With stabilization method, without stabilization methods, maybe I can reach somewhere around here. But after that, as soon as plasma instabilities complicate the things, there are non-linearities, and in that case, stabilized algorithm is needed in order to make that simulation feasible on the chosen grid. And now, how should I know that these simulations are physical? Here we look at the sketch, which depicts the experimental observation. This pink curve denotes the evolution of plasma energy, and here we see sudden decrease in plasma energy. This stage is known as thermal quench that we observe here. And at the end of thermal quench, we have a spike in plasma current. We also see this spike here. So these are only qualitative validations. We are still working on quantitative validations of this work against the experimental data. So these are some statistics that what effect the stabilized methods has. The first column denotes C, which is a scaling factor for shock capturing stabilization. So C0 means that C0 means I'm not using shock capturing stabilization, and 1, 10, 50 means I'm scaling the stabilization with that number. Second column denotes the number of time steps needed to reach simulation time around 1.5 milliseconds. During each third column denotes the average time required for 1 GMRS solve to converge during each simulation. And if I multiply these two columns, I get some estimate of the time taken by the simulation, or precisely by the GMRS solver. So we see to reach time t is equal to 1.5, simulation takes more than 13 hours, but with shock capturing stabilization, it takes less and less time. So what is the impact of this work? First of all, the numerical techniques that we have developed, they are applicable to large class of hyperbolic partial differential equations, but we demonstrated their use for fusion plasma application. One of the urgent problem faced by fusion plasma program. The simulations were performed for jet tokamak, but the same algorithm can also be used for ITER and demo to study the ITER and demo, which are significantly bigger than the jet tokamak. The ongoing work right now is the treatment of other kind of singularities that we just talked about few moments before. And we are also looking at the HPC profiling aspect of the code, because these simulations are, even with the stabilized finite element methods, these simulations are very time consuming. They take order of months. So we are interested in what is in looking what is going on at the HPC level. These are my funding and support organizations. And finally, I thank you for your attention.
Audience and questions.
Profiling, you are doing the last slide you were saying.
Yeah.
kind of so anything you have tried for profiling?
And
I mean,
can you
what
please-
did you try in profiling? Did you see the solver time or overall the simulation? And your GM race is just solving the linear equation. So, I mean, just I'm asking what kind of profiling you are doing.
So for GMRS, I have not used any profiling. Right now, we have just begun the work where we will use profilers like Tau,
Ah,
Harshan.
okay. So you will see the overall time.
Overall,
Just
yes, yes.
okay. Down. And but you know GMRS is slower than other solvers, iterative solvers. So did you try other solvers which are a little bit faster than GMRS? Is very general minimal residual. No,
Yeah,
you take every kind of things. But if
Yeah.
you know their specific property of your matrix and all, then you can choose some method which is faster than this, faster convergence.
yes. So GMRS, so a lot depends on the preconditioners here.
Mm-hmm.
Jorac has its own preconditioners designed
Okay.
because of the periodic direction is handled by spectral methods,
Oh.
Fourier spectral methods. So
Oh,
they have
so
their
it's
own
hybrid.
preconditioner.
Okay.
So
Okay.
solver is pretty much fixed.
Okay.
All I can do as a user of linear solver, all I can do is to
No,
maybe
then it's a different situation. It's not a
Yeah.
pure finite element. You are having hybrid spectral and finite element both. So
yes,
it's a
exactly.
different situation.
Yes.
No? Okay. Yeah. Bye.
Yeah, anyone else? Any other question? Okay. So if not, then let us thank Dr. Ashish Bhole for this enlightening talk.
Thank you.
We can all have tea in the next room.
Yeah.
Also, they might be having some sort of